Hey y'all, Rusty Rob here. Welcome to another video. Today we've got an exciting problem from MetaHacker Cup, and we'll go through one of Gennady's solutions. For those of you who don't know, Gennady is one of the best programmers in the world. He's won the world finals of programming many times, as well as Google Code Jam. Even from a young age, he was winning many competitions. So this is him. Yeah, I'll just get rid of my video so you can see. There you go. So yeah, this is him here. And you can see, yeah, he's won a lot of contests. So we can learn a lot from reading through his C++ code and trying to rewrite it in Rust, maybe get some insights into how Rust and C++ compare. You can see he's submitted his first solution in 12 minutes and his second one in 13 minutes. And he used the same code for both the first two problems. So let's open up that second problem. So in this problem, you're given like an array of numbers and an interval from left to right, which is like a subsequence of the array. And you essentially want to know, can you delete a number from that interval such that the left half can be shuffled to be equal to the right half? So yeah, I'll link this problem in the description, but yeah, feel free to have a read through it. And so I've had a read through his code, and he's using a Fenwick tree, which he probably would have copied and pasted in to save time on typing. And he's using this method here, which generates random integers. And yeah, he's generating a bunch of random numbers, I think up to 1 million random numbers. Each of these numbers can be from 1 to 1 million, and the length of this array can be up to 1 million. I should have also mentioned, yeah, you've got 85 test cases, and each test case, yeah, has up to 1 million numbers between 1 and 1 million. But then you also have up to 1 million queries. So it's not just one interval that we're concerned about, otherwise it would make this a bit too easy. It's any interval. And to make it even more difficult, some of the queries update the array and change the numbers. So you can't like do much pre-computation and things like that. So yeah, where is it? So either you get a query of type 1 where you change value xi to yi, or you get a query of type 2 where it's asking, is it possible to remove a number in the range from left to right such that the left half can be shuffled to equal the right half? And yeah, so he goes through each test case, creates a Fenwick tree, initializes that Fenwick tree, and then he goes through each query. Based on the type of the query, he just updates the Fenwick tree, or he gets the answer using the Fenwick tree. So yeah, this code might be a bit hard to understand, so let's just have a look in xCalidraw to get a kind of an idea of how we could solve the problem, and then it'll help us understand his solution. So let's say this was the numbers given. Then let's think of an easier problem. What if instead of worrying about removing a number, let's just say we want to check if two sections of the array are the same. So we want to check this section and this section are the same. So we can see here we've got two ones, a 2 and a 5, and in this other box we've got two ones, a 2 and a 5, and they both have the same total. So that total kind of gives us a hint. Oh, maybe we just want to look for where the total is 9, right? And then maybe they're more likely to be the same. If the total is not the same, then we know they're not the same. But Unfortunately, over here we have 5 and 4, which also add up to 9, and obviously this can't be shuffled to equal this set of numbers. But we're on the right track, so we need to find a way to fix it so that we don't get these false positives, so we don't get these kind of collisions. And then we also need to find a way to calculate these totals efficiently. So if we use the prefix array, like a cumulative frequency, then we start with 0, we add 1, then we add 2 to get 3, we add 1 to get 4, and so on. Then we can just, to work out this total of 9, we can just go 9 minus 0. And to work out this total of 9, we can just go 38 minus 29, and so on. So a prefix array could efficiently give us the totals, but we have that problem where there's some of the queries are updating this array. And to update the prefix sums, if we update one of these numbers, then we have to update all the numbers after that. So updating that would cost order n per query, so it's not feasible. But that's where we can use a Fenwick tree. So a Fenwick tree or binary indexed tree is got log n updates and reads. So that's going to be quick. So now, how do we make sure that we don't get any totals the same? Well, if we use really massive numbers, the chance of them adding together to equal another number is quite small. So think of it, if you have like a UUID plus a UUID is kind of equal to a UUID itself, right? So if we mapped each of these numbers to like a massive random number, then yeah, if we add one set of random numbers and another set of random numbers together, it's really unlikely they'll have the same total unless they're the exact same frequency of each random number within each of those sets. The problem with that is if we're adding together like up to 1 million random numbers, we could get int overflow, right? So there's two things to consider: is how do we avoid overflows? So you could use modular arithmetic maybe. We're not going to do that, and Gennady didn't do that in his solution, I don't think. First, let's talk about the birthday spacing problem first. So the birthday paradox is that counterintuitively, the probability of a shared birthday exceeds 50% in a group of only 23 people. So if you think about you're in a room of like, 2 people, it's unlikely you have the same birthday. But as you keep adding people, so you've got 365 days. So each of these is like a 1 in 365 chance of colliding. But each time you add a new person, the chance of the birthday colliding with any of the other birthdays increases, and eventually, after about 23 people, you're quite likely to have 2 people with a birthday on the same day. So for us, we really want to avoid collisions so that we avoid, these false positives. So, but we also want to avoid overflows, right? So let's just use the biggest numbers possible. So let's say they all add up and it fits inside an I64, which is 2 to the power of 64. Well, then that is around about 10 to the power of 9. And so our maximum value, let's say it was repeated 10 to the power of 6 times because we're adding up all of them, and let's say they're just all equal to that, then that needs to add up to less than this to avoid an overflow, which means our maximum value needs to be roughly equal to 10 to the power of 13. And then how do we avoid a collision? Well, each number, instead of 365 days, we've got 10 to the power of 13 days, right? So there's a 1 in 10 to the power of 13 chance of a collision, but we're doing about 10 to the power of 6 operations, which means this is our chance of collision. So there's about a 1 in 10 million chance that we're going to get a collision and we're going to get the wrong answer. And then I guess you multiply that by 85 test cases as well. So this is maybe, I don't know, 5 or 6 or something like that. And so I'm happy to take my chances. I don't know if you're like a gambling person or not. You could always do it twice or something like that. Have 2 trees or something. It'll be like twice as slow, but your chances will go up. But yeah, so we're happy with that. And so this is kind of the approach Gennady's taken. So each of these numbers that are in the input, we just map that to like a random number. So there'll be like a massive random number for 2. There'll be one that's the same for like 1, and so on. And yeah, so look up Fenwick tree if you're not sure about it. It's a really cool algorithm. I won't go into that. So let's have a look at the code. First of all, I'll just run this. So you can see it's running in less than a second if I'm not recording a video. So yeah, that's pretty quick. So we had, I think there's 6 minutes to run your code and submit it, and we're running in about a second or less. So this is pretty quick, this code. And there's a slight difference in my implementation to Gennady's, but they're reasonably similar. So he's basically just generating these random numbers. So for each of the possible values that are in the array from 1 to a million, we get a random number. And you can see I've done something similar here, where I've generated a random number from 0 to 10 to the power of 13 in Rust. So I've just imported this thread range and range, and I just had to add this dependency here because it's not part of the standard library for now. And yeah, so Gennady's assigning all to all these coefficients, all these random numbers, but and sorting that. The only reason for that was just later on he uses lower bound. So it's just to check if a random number is within that set of numbers. So I should say, in this example, we've just been looking for 2 sets that are equal, but we actually need to consider, we need to remove one number, right? So if we look at this set versus this set, we could remove the 20. So if we look at, 29, if we added 20 to the total, we'd have 29 and 9. And so the difference between 29 and 9 is 20. And we could look at 20 and be like, is 20 one of those random numbers we generated? Yeah, it is. Okay. That means we could have removed it. So instead of checking if the sets are exactly equal, we're seeing if they're equal but off by 1. And this could actually be pretty useful at Thread at the company I work at, because we have production lines where you have hundreds of conveyor belts and you have first products rolling down the production line. And so between different areas within the factory, you might want to know what products are there at a given point of time. And you want to say, have I ever seen this situation with these exact set of products before, and maybe you could use that to predict how long or how much congestion there's going to be in your production line. So that's getting into kind of process mining and things like that. But yeah, so let's just go back to the code. So he's basically got a million random numbers, and then for each test case, so he's reading the test case here, number of test cases. He's just outputting the case number. Then for each, so he's inputting how many numbers there are in that test case, and then he's reading all of those numbers into a vector of integers. Then he's creating a Fenwick tree, and then he's, for each of those values he read before, he is mapping that value to a corresponding random number. So if it was like a 3, then I had one like the third random number or fourth random number. And so now using this Fenwick tree, he can easily, see the total from left to right of any interval, and that will give him a sense of what numbers there currently are there, and he can compare that to another interval. Now he's reading the number of queries, so there's a million queries it's going through, and let's an operation 2. He's reading the operation. So if it's a 2, then that's a query from left to right. Let's just look at operation 1 first. So if it's an operation 1, then it's an update. So in that case, we're changing the value at position X to a value of Y. So he's subtracting 1 because, and the problem, the numbers are from 1 to n, whereas as an array index, you want it from 0 to n minus 1. So that's why he's using zero-based indexing, which is what you do as a programmer. And so he's modifying. So what's he doing? He's adding the random number corresponding to the new y value, but he's subtracting what was already there before because that's no longer there. So he's keeping track in the original array of what the current value is. So that's why he's taking that away. And otherwise, if the command is a 2, then he's just reading L and R, which are 1-based indexed. And then this is kind of interesting here. I think you can learn a lot from this. He's subtracting 1 from the left side, but not from the right side. And in programming, you often have an open interval on the right-hand side, but basically, when you do a for loop, you'll be like, for I equals 0, I less than n, I plus plus or whatever. You don't go I less than or equal to n. And that's quite powerful in a lot of situations. It also helps you avoid underflows and things like that, because if you've got an unsigned integer, you can't really go -1 because it will overflow. So I always recommend going from 0 ... to n and not to equal n. That's the Rust syntax. And this is helpful, like just to get the length of that interval. It's just r minus l. Whereas if he'd gone, minus r, then he'd have to go r minus l plus 1 to get the length. And there's just lots of little things where it helps. So now, if the length is odd, because if the length is even, you can't remove a number and have them equal, right? And then here he's just using a for loop because he wants to know, am I removing a number from the left side or from the right side? Um, so, so yeah, one of these two intervals will be one bigger than the other interval. So he's just taking the difference. Um, and then he's just checking, was that difference a valid random number that he generated? Because then that can be removed to make the two intervals equal. And so here, this lower bound is just a binary search. So you can do lower bound in Rust. In Rust, you have binary search, and you also have partition point. So there's quite a few useful methods there. But in my implementation, I'm just using a hash set to see if it exists or not. And then, yeah, if it was okay, then it just increases the number of valid intervals and prints that out. So yeah, it's reasonably straightforward, but still pretty impressive to code that up. And you know, I guess if you give him time to read the problem and things like that and submit, he probably coded this up in less than 10 minutes. So yeah, it's pretty, maybe even like 7 or 8 minutes. So it's pretty impressive. Um, and so if we go through the Rust code, you can see it's pretty much the same. Um, using a little bit more memory because I clone everything into this hash set. But yeah, it's just a bit easier. I'm using this Fenwick tree, which just takes in a closure which generates the value at each location. And I'm just starting every value off at 0. But actually what I could have done here is I could have probably gone like S, I could have gone like next, it's a S dot next or something potentially. Could have done something fancy like that. No, actually no. I think you just want everything as 0. I think maybe if you overload your type to use multiplication, then maybe you'd want everything to start off as 1. Since we're using addition, we'll just start everything off as 0. And we're iterating. So we're basically, what did we do? So we're just initializing our array of numbers to 0. And then we're iterating that in a mutable way with mutable references. And enumerate just give us the index as well, so we can update the tree. And so we're just setting that value to G, which is just a closure of created that gets the next number. And yeah, we're just adding the random value associated with that to the Fenwick tree. And then here, if it's an update, we're just getting X and Y and updating it exactly the same way. And luckily, the Fenwick tree we're using, it uses an open closed interval as well, which is quite cool. So it's going to work for us. That's more relevant down here. And we're just keeping track of what the current value is at each location. And yeah, when we get an interval left or right, we're just unpacking this tuple and yeah, subtracting 1 to get 0-based indexing. Same again, checking if the size is even or odd. And then we're looking at the two possible midpoints. We're getting the sum of the left interval and the right interval. We're looking at the difference. So here I just took the maximum minus the minimum. And I check, is this different in our hash set of random numbers? And if it does contain it, then the answer increases by 1, and we just break so that we don't double count for a particular interval. And yeah, that's pretty much it. So that was an interesting problem, and yeah, it's cool that you can kind of check if two huge sequences of numbers are similar to each other by using a hash function, but still modify numbers within those intervals and your hash function to remain valid afterwards. So it's kind of the power of these random numbers and the Fenwick tree kind of combined. So yeah, thanks for watching the video, and check the description for the code. And yeah, have a good day.